This leads up naturally to our collaboration on the AGI board, really. I've been fascinated by Kanerva's sparse distributed memory for a long time. Played around with my own implementations and was interested to see what Stan Franklin was doing with it in LIDA. And I've been thinking about introducing it into Opencog architecture as an infrastructure for episodic memory, actually. I mean, possibly for other things as well. And there's enough videos with me explaining Opencog out there. I'm not going to go into great depth on that, but I mean, we have a knowledge hypergraph or weighted labeled knowledge metagraph, which lives in RAM across many machines. And there's many different learning algorithms and reasoning algorithms that act on it sort of concurrently, using it as a big shared long and short-term memory. So we combine neural nets, evolutionary learning, and probabilistic reasoning and so forth. But we're rebuilding Opencog into a new system called Hyperion. Part of it's for greater scalability and flexibility and usability and speed. But another design goal with Hyperion is to make it easier to connect Opencog with other cognitive components, which could be a deep neural net, or it could be a hypervector-based AI system, right? So having a hypervector-based AI system for episodic memory, for managing the long-term, like life history, biographical memory of a robot, like our friend Grace here, who we'll let talk soon, or any other kind of AI system. I mean, I think seemed very interesting. Not by any means not the only thing you can do with the hypervector system. It's just what it popped into my head, because deep neural nets are okay now at perception. They're okay at robotic movement. They're terrible at abstract reasoning and thinking, but I think my probabilistic logic engines are good at that. Neither probabilistic logic nor deep neural nets seem any good at episodic memory, and it seemed that could be a place where hypervectors would shine. So, yeah, another aspect of our collaboration, just to introduce to the audience, is I've been thinking for a while about how to make a chip to accelerate Opencog type architecture, and the processing bottleneck in Opencog is really graph pattern matching, or more generally metagraph pattern matching. Like you have an abstract pattern, a template to be matched, and you want to search through the knowledge metagraph to find everything that matches. I mean, it could be something simple and concrete, like find me nodes and links that are about like silly American people who drink too much coffee, right? And then you want to search the knowledge metagraph to find all knowledge it has about silly Americans who drink too much coffee. Or it could be much more abstract knowledge, like find me a piece of programmatic procedures that match this sort of mathematical constraint, and you want to find all those procedures. So that you wind up spending 90% or more of your processing time just looking to match patterns against this knowledge graph. So I came up with a design for a chip that, if you put the knowledge graph in RAM on that chip, then matching patterns against the knowledge graph on the chip would be very, very fast compared to if you're doing it in software. And as we talked, it seemed it could be interesting to make a sort of board that has my Opencog pattern matching chip, your hypervector chip, maybe a deep learning chip, a conventional CPU, maybe some additional hardware to do crypto and homomorphic encryption to allow secure computing to be done, and wire these together with fast processor-to-processor interconnects on the same chip. Then, hey, maybe you have an AGI board, that can do for general intelligence what GPUs have done for deep neural nets, right? Because, I mean, you could do most of what's now being done with deep neural nets on CPUs, but for the research and for fine-tuning the models and for just understanding what architectures to use, the fact that you could do really fast experiments on multi-GPU boards was really important, even if you don't need those multi-GPU boards to deploy the final systems. And in a similar way, I think for your hypervector systems and for my Opencog Hyperion system, I mean, having optimized hardware, it can lead to more inexpensively deployable systems. But it can also speed up a lot of the research and figuring out exactly what systems you want to build. And yeah, so toward that end, we've been working on a partnership between Simuli and then True AGI, which is a spin-off of SingularityNet, my decentralized blockchain AI project, focused on commercial deployments of Opencog Hyperion. We've been working on a partnership between True AGI and Simuli to work on the pattern matching chip and on an AGI board, combining the pattern matching chip with the hypervector chip. And I think this could be used for a lot of different experimentation, right? Like we could experiment with Opencog Hyperion with the core bits running in hardware. You can experiment with Andrew Coward's recommendation system using the hypervectors as a very clever data structure to speed up operations there and make it more feasible on current hardware. And there can also be open-ended research. I mean, we can look at new AGI architectures that combine different elements here.